For our next example, we are looking about golf balls. They are supposed to have a standard deviation that does not exceed 0.08 ounces. So quality control inspectors say the machines need to be recalibrated because he thinks that the standard deviations is more than 0.08. So he thinks that maybe the machines are a little bit off. But they don't want to spend all the money to adjust the machines if they don't need to. So we're going to run a test. He selects a simple random sample of 30 golf balls off the assembly line and finds that they have a mean weight of 1.62 ounces, which we actually don't care about, and a standard deviation of 0.0804 ounces. So we want to know, does that support the need for recalibration at the 0.05 level of significance? And we are going to assume that the weights are normally distributed. So step one is to write down our null and alternative hypothesis. So our quality control guy thinks that the standard deviation is more than 0.08. Notice this time we are talking about standard deviation, not variance, so it's not squared. Standard deviation is just sigma. So he thinks it's greater than 0.08 and we need to recalibrate. The null hypothesis is that it's less than or equal to 0.08 and the machines are just fine. All right, step two. Since we're talking about standard deviation or variance, this is still a chi-squared test. And we have that alpha is, what was it, 0.05? Okay, we're going to calculate our test statistic. So chi-squared is, sorry about that equal sign, n minus 1 s squared over sigma squared. So let's see. He tested 30 balls, so 30 minus 1. And in that, the standard deviation was 0.0804 squared over, and we need sigma squared. Now this time our null hypothesis is just sigma, so we do need to square it this time. So just pay attention to whether or not you need to square that. Okay, so when we put this all in our calculator, I got 29.291. Okay, so that's our calculated test statistic. So now we need to find the critical values. Let's see, our alternative hypothesis is greater than, so this is going to be a right-tailed test. And our degrees of freedom is 29, which I believe is on the table. I think it does go up that high. Okay, so for a right-tailed test, we are looking for chi-squared of our alpha level. Okay, and you can double check that in the rejection region box. So 0.05. So take a look at your table at the row that says 29. You're looking for 0.05, and we get 42.557. So let's take a look at what this looks like. This is a right-tailed test. So here's our shaded. And this value right here is 42.557. So anything that we get that's above that would be in the rejection region. Our value is 29. That is clearly not in the rejection region. So our step 4, since we're not in the rejection region, we are going to fail to reject. Okay, so what does this mean? This means at the 0.05 level of significance, I'm going to abbreviate that because I ran out of room. The data does not support that the standard deviation is more than 0.08. Okay, it appears that it's less than or equal to 0.08, so the machines are fine. So we're going to say the data does not support that the machines need recalibrated. which is good news for the factory because they don't want to spend the money to recalibrate the machines if they don't have to. And according to our test, they don't have to.